Welcome to this lesson on circular motion. In this video, we will explore the fascinating world of motion along curved paths and learn about angular quantities. Circular motion is all around us, from planets orbiting the sun to wheels spinning on vehicles. Understanding circular motion opens up a deeper appreciation of how objects move in our universe. Let's begin our journey into this exciting topic. Circular motion is the motion of an object along a circular path or curved trajectory around a fixed point. The key characteristic of circular motion is that the distance from the center remains constant throughout the movement. Even though an object may move at constant speed, its velocity direction is constantly changing because velocity is a vector quantity that includes both speed and direction. This continuous change in direction is what makes circular motion unique and interesting to study. To describe circular motion, we use angular quantities. Angular position, represented by the Greek letter theta, is the angle between a reference line and the position of the object. It is calculated by dividing the arc length s by the radius r and is measured in radians. Angular displacement, represented by delta theta, is the change in angular position as the object moves along the circular path. It is found by subtracting the initial angular position from the final angular position. These concepts help us precisely describe where an object is and how far it has moved along its circular path. Angular velocity describes the rate of change of angular position with respect to time. Represented by the Greek letter omega, angular velocity tells us how fast something is rotating. The formula is omega equals delta theta divided by delta t, and it is measured in radians per second. An important property of angular velocity is that its direction is perpendicular to the plane of rotation. When all points on a rotating object have the same angular velocity, they share the same rate of rotation, even though points farther from the center move faster in terms of linear speed. Angular acceleration, represented by the Greek letter alpha, is the rate of change of angular velocity with respect to time. The formula is alpha equals delta omega divided by delta t, measured in radians per second squared. Angular acceleration indicates how quickly the rotation speeds up or slows down. When an object starts spinning from rest, or when a spinning object comes to a stop, angular acceleration is at work. Understanding angular acceleration helps us analyze situations where rotational motion is changing, such as a spinning top gradually slowing down due to friction. Linear and angular quantities are closely connected through the radius of the circular path. The arc length s equals r times theta, showing how linear distance relates to angular position. Linear velocity v equals r times omega, connecting how fast something moves along the path to how fast it rotates. Linear acceleration, A equals r times alpha, relating linear and angular acceleration. These relationships are fundamental because they allow us to convert between the familiar linear measurements and the angular measurements used to describe rotation. The radius acts as the conversion factor between these two perspectives of the same motion. Centripetal acceleration is the acceleration directed toward the center of the circular path that keeps an object moving in a circle. There are two common formulas for centripetal acceleration. The first is a sub c equals v squared divided by r, where v is the linear velocity and r is the radius. The second formula is a sub c equals omega squared times r, using angular velocity. A crucial point to remember is that centripetal acceleration always points toward the center of the circle. This inward acceleration is what continuously changes the direction of the object's velocity, keeping it on its circular path rather than flying off in a straight line. Centripetal force is the net force required to keep an object moving in a circular path. The formula is F sub c equals m times v squared divided by r, where m is the mass, v is the velocity, and r is the radius. This force is always directed toward the center of the circle. Different situations provide centripetal force in different ways. For planets orbiting the sun, gravity provides the centripetal force. On amusement park rides, the normal force from the seat or walls provides it. When swinging an object on a string, tension in the string provides the centripetal force. Without this center-seeking force, objects would move in straight lines instead of circular paths. Period and frequency are two related concepts that describe how often circular motion repeats. Period, represented by capital T, is the time required for one complete revolution. It can be calculated using the formula T equals 2 pi r divided by v. Frequency, represented by F, is the number of revolutions per unit time, and equals 1 divided by T. These quantities are inversely related, meaning when one increases, the other decreases. Angular velocity connects to both through the relationship omega equals 2 pi f, which also equals 2 pi divided by t. These formulas help us understand the timing and repetition in circular motion. Uniform circular motion is a special case where an object moves in a circle at constant speed. In uniform circular motion, three key characteristics exist. First, the speed remains constant throughout the motion. Second, even though speed is constant, the velocity direction continuously changes because velocity includes direction. Third, the angular velocity remains constant. An important and sometimes surprising fact is that even with constant speed, acceleration exists due to the changing direction of velocity. This acceleration is the centripetal acceleration we discussed earlier, always pointing toward the center and keeping the object on its circular path. Circular motion appears throughout nature and technology. Planetary orbits demonstrate circular motion on a cosmic scale, with planets orbiting the Sun in elliptical paths governed by gravitational force. Ferris wheels provide circular motion experiences at amusement parks, where passengers feel changing forces as they rotate. On curved roads, banking helps vehicles navigate turns safely by providing the necessary centripetal force through the road's angle. At the atomic level, electrons move around atomic nuclei in patterns described by circular motion principles. These examples show that understanding circular motion helps us comprehend phenomena ranging from the smallest particles to the largest celestial bodies. Let's review the key concepts from this lesson on circular motion. First, angular quantities including angular position, angular velocity, and angular acceleration are essential tools for describing rotational motion. Second, linear and angular quantities are connected through the radius of the circular path, allowing us to translate between these two perspectives. Third, centripetal force is the center-seeking force that keeps objects moving in circular paths, whether that force comes from gravity, tension, or other sources. Finally, remember that even when an object moves at constant speed in a circle, acceleration still exists because the direction is constantly changing. Mastering these fundamentals of circular motion provides a foundation for understanding more complex rotational dynamics.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.